So the topic for today is uh, application real life, not application. Let's not term it application. Let's term it as examples of real depth and apparent depth. Okay. So the first example is, I tell this every time, apparent bending of a stick under water. It's very simple. You have a vessel that has some water in it. Now what we do is, it has some water, like let's say in this level till this level. Then we have a stick that is immersed inside the water. So we have a stick that is immersed inside the water. Now what will we as observers notice, like what will the stick look like to us from outside? So this is a denser medium. And this is a rarer medium, right? Rarer medium, because this is air and this is water. Now we have our eye somewhere here. We are watching it from here, right? And let us draw the rays that comes out. So let us assume that there is one ray coming out. There is one ray coming out from this point to here, and another ray that is coming from here to here. Now we'll draw normal. Normal for the second case. Now we know that since the ray of light is coming from a denser medium to a rarer medium, it will bend away from the normal, and this will also bend away from the normal, right? So bend away, bend it away from the normal. This will also bend away from the normal. Now I'll change the eye position. So my eye is somewhere here now, watching it here. Now if I produce this line backwards, I'll find that these two lines come and meet somewhere here. Not exactly on this line itself, it will be a little bit raised. And here these lines will meet somewhere here, which means the stick will appear a little bit raised to us, like so. So for us the stick will be somewhere here. So if AB is the stick, so we'll notice it as AB dash, because the light rays coming from B will go to the interface between the two media, right? And since it is coming from a denser medium and is going to a rarer medium, it will bend away from the normal. The second ray will also bend away from the normal. Now these two lines, when produced back, will meet somewhere at B dash, right? Somewhere at B dash, and what we see is A. Let's say this point as O. We see AO B dash. We don't see AOB. We don't see the stick straight inside the water. We see the stick a little bit bent and deformed. So we'll not see the stick to be straight as well. So till the stick reaches the interface of water, it remains straight. After it touches the water and enters it, it'll be a little bit bent upwards. So it'll be straight and then bent a little bit upwards. So that is the application. That is the example of a real depth and apparent depth. So this is actually the real depth. So which one is the real depth? So this one is the real depth till B, and this one is the apparent depth, that is still b dash. So this is apparent depth and this is real depth. So this is the apparent bending of a stick underwater. So when you put the stick inside water, the rays of light coming from this end of the stick gets bent away from the normal. So it bends away from the normal, because of which our eye assumes that the light is coming from somewhere here. That is why we find the stick to be bent a little bit upwards. This is proper application of refraction. This is a proper and best example of refraction. So is this clear? Apparent bending of a stick inside water.
Why are there two beams?
हजुर के भन्यो?
दुईटा बीम किन छ?
एउटा बनाउँदा नि हुन्छ, तर मैले चाहिँ किन दुईटा बनाएको भने I wanted a point where the two light meet to be the point where B is there. So why did I make two rays is because I wanted the two rays to meet so that when they meet I can assume this point to be B. So यहाँ पनि दुईटा, the two rays are coming from the same point, right? Which means one point is giving out two light rays. So now this light ray should come back and meet at some point, and when both the light ray meet, there should be one point only. So you can make it as a single light ray as well, no problem. Will not be any problem. You can make it as a single light ray, but the only problem will be you'll not be able to find where the light will meet, where the image will be found. So since I have two rays, so I can easily conclude that wherever the light ray crosses each other, wherever the light ray meet, there the image will be formed. There, that will be the point where we can see the image. Okay, so if you use a single ray, so if I give it, yes.
अनि नि त्यो उयो जब त्यो बीम मिट हुँदैछ नि हामीले हिजो जस्तै कोइनमा चाहिँ उतै गएर टच भयो नि अब
we
त्यो होल लाइनमै गएर
correct
टच भयो नि
correct
त्यसमा चाहिँ किन टच नभएको त्यो उयो
मतलब why are we not going close? So we can go close, no problem. We can go close only. तर यो त चेन्ज हुँदैन नि त, right? This B and B is directly above each other. So even if you come close, this will not change. यो चेन्ज हुँदैन. तिमी पानीको छेउमा आयो भने you'll see the bending, right? Have you tried it? Have you tried looking at it? So when you put a stick inside and just look at it, you can see the bending anywhere, right? You can see it from any angle. So, except from one angle, because at one point if the light ray just goes straight above, right, if you see from straight above, you'll not see the bending, because it'll go straight up, and when something goes straight into the normal, it will not bend. Refraction will not happen, right, if the light goes straight into the normal. So interface ma, if something is coming straight into the normal, even if this is a rarer medium and this is a denser medium, the light ray will not bend, right, if it is coming at an angle 90 degree, right? So if you see the thing directly above at some angle, you will not see the bending. That is because the ray of light is coming directly straight into the normal. But that too is not possible. You'll always see the bending, because bending always happens because the light is always coming from a denser to a rarer medium. And why I'm using these two light rays, that is only because I want to find the point where the image is being formed, where the apparent image of the point B can be seen by us. So there's no other reason for using two. I can use 3, I can use 4, it doesn't matter. So even if I use 3, so I can do something like this. So I can do something like this, and this light will also come back and meet at the same point. So I can use 3, I can use 4, I can use 2. But only problem of using 1 is we can't find exactly where the image will be found, where the apparent image of B will be found, right? So where will be the apparent position of B? Because one light ray means we can't exactly find where the image will be found. If two light rays are there, then the point where the two light rays intersect will be the point where the image is formed. Okay, so that is the reason why I use 2. We can use 3, 4, any number you want. Anything else? Okay. So this is a simple application. There is one more application. So looking something from inside the water, like for example, if a fish tries to look from inside the water to a bird that is flying outside, so what will the fish see? So let's say I have a container and I have a fish inside, right? And the fish is seeing a bird somewhere outside here. Let's say the bird is somewhere here. Okay, so we have a bird here at this point. We have the bird here, that is, let's say, object. Now we have a fish somewhere inside, right? So what will happen now? So when I project a light ray, from the bird, right, I make a normal at the interface. Now what will happen? The light will bend. Since this is a rarer medium, and this is a denser medium, the light ray will bend towards the normal. So since the light ray will bend towards the normal, I can make the light ray something like this, right? So it's bending towards the normal. So let us say that the fish is somewhere here. And fish is looking straight into this point. Now since the fish is looking straight up, this light ray will not look bent to the fish. The fish will see the bird somewhere here. So this will be the image of the bird. Somewhere here. This will be the object, that is the bird, and this is a fish that is looking from inside the tank. So what happens is the light ray from the bird comes in, goes to the fish's eye. When the fish looks through, the fish will not see the bend, it'll rather see the light ray going straight, and it'll find that the bird is at a higher, right, it's at a height higher than actually it is. So which means this is the real depth, this is the apparent depth. So this is the real depth, this is the apparent depth. So it is not always necessary that apparent depth is shorter than the real depth. So in all the cases that I did from yesterday, and like the question that I solved yesterday, the derivation, and the one that I did previously here, that is this one, apparent bending of light, apparent bending of a stick. So here we can easily conclude that the real depth is longer. It is the depth is deeper than the apparent depth, right? The actual depth is more than the apparent depth, but there are cases where the apparent depth is more than the real depth. So here clearly we know that the apparent depth will be more than the real depth, right? The bird is actually at a shorter distance or shorter height from the surface of water, but the fish assumes it to be at a height higher than it actually is. So this is also an example of real depth and apparent depth. So is there any doubt? Anyone?
apparent depth भनेको चाहिँ यो जब हामीले refracted rayलाई चाहिँ हामीले backwards जब produce गर्छ
apparent depth is what you see to be correct. So when a stick is inside water, you see the stick to be bent, right? So that is apparent for you. That is what you are seeing. Apparent भनेको which may be correct. Okay, apparently, which means you are seeing it, right? That's why you are saying apparently. It may or may not be correct. So apparent भनेको चाहिँ what you are seeing, right? It may be true, it may be real, it may not be real. But in refraction, in case of refraction, the apparent depth is not equal to the real depth. So when there are two different media, then apparent depth and real depth are totally different. So apparent depth is what you see, and real depth is real depth is the one that actually is. Like when you dip a stick inside water, the stick doesn't bend, right? The stick will not bend. Stick will remain the same. Like if it is a straight stick, it'll go inside and it'll remain a straight stick. Once you put a stick inside water, there is no theory that the stick will bend, right? The bending is just happening because of the phenomenon called refraction, and your eye is seeing the stick to bend in the upward direction, in a particular height, in a particular distance, whatever it is. So that what you see, what your eye notices, आँखाले देख्ने कुरालाई चाहिँ apparent भन्छ. So that is apparent depth. Real depth is the actual depth that the stick travels when you put it inside the water. So it will not actually bend, right? It will just go in. So that is real depth. And apparent depth is what you see. Okay? Anything else? Anything else? Nothing? So this is the end of this part. There is a thing written. Yes, Vanada.
अब यो तपाईले फिशको भन्नुभयो नि यो वाला यसमा बर्डले हेर्दाखेरि चाहिँ फिशको चाहिँ के हुन्छ
Bird layer. Okay, nice. Bird layer will be the same thing as this apparent bending of stick. So now this is the bird, this is the fish, right? This is the actual fish, correct? So this is the fish, this is the bird. Now the bird will see the fish a little bit higher. Okay. So this you just need to replace this entire stick with a point B only. Just delete this entire stick. Just put a point B here, and just do the same exact diagram. Make a single ray, double ray, triple ray, whatever you want, and project the ray backward at a point. So you'll clearly find that the bird will see the fish a little bit higher than actually where it is. Right? It'll be a little bit closer to the surface than what it actually is. So the fish will find it that way. I mean, the bird will find the fish in that position, and the fish will find the bird in that position. So these are basically used by the birds that actually scavenge on fishes, right? So there are some birds that go and catch fishes inside water, right? So they are used to it. They are genetically engineered to know about this thing. Maybe that's why they can so accurately go and catch the fish. Though the apparent bending of fish is always possible, always happens inside water, right? The fish will be at a depth shorter than what it actually is. So it'll be a little bit lower than where it actually appears for the bird. So bird will find the fish to be a little bit higher, closer to the surface. So the bird may think that it is easier for the bird to catch the fish, but the bird is genetically engineered that way. Many years of evolution made the bird like totally able to catch the fish, even though the phenomenon of refraction keeps on happening, right? Real depth and apparent depth is always there, but still the bird is able to catch the fish, right? Though the fish may look higher to the bird, but the bird will still be able to calculate and catch the fish. So that happens in nature. It always happens. And this is, I have never heard about fish looking at a bird, but this, if fish actually looks into bird, this is what the fish will look at. So if the bird is flying at like a height which is closer to the surface of water, the fish will find the bird to be flying at a height higher than the actual height. Okay, so this is the application of
यसमा चाहिँ अब्जेक्ट अब त्यति बेला फिशले हेरेको बेलामा चाहिँ अब्जेक्ट अब के फिशले हेरेको बेलामा चाहिँ लाइट चाहिँ उतेबाट हुन्छ है, लाइक इन्सिडेन्ट चाहिँ बोर्डमा हुन्छ है.
अगर फिशले हेर्दैछ भने जुन चिजलाई हेर्दैछ त्यहाँबाट आउनुपर्छ लाइट. सो इफ यु आर लुकिङ एट द मुन, your eye should not send the light, the moon should send the light, right? Only then you can see the moon. तिमीहरुको आँखाबाट मुनमा लाइट गयो भने त it will be like a flashlight thing. So only where you put the light you see the things. But when you look at the sky, you can see the moon, the stars, and all those things, right? Because all these things are sending light at you at like together. So you can notice that some light is little bit, some of the light is brighter, some is not, right? So the thing is, whatever you're looking at, that thing should emit light so that you can see it. It's not that you have to emit light. Okay, so if the fish is looking at a bird, then bird should emit the light. Okay. You can look at something only when it can reflect light. So you can see the color of your wall only if the wall can reflect the light that is there in the room, or from the sun, or from the light that you turn on by pressing on the switch. Yes, yes.
तपाईको नि यो माथि बोर्डले हेरेकोबाट लाइट जाने छ नि, त्यो गएर बेन्ड भएन?
भइरहेको छ त, अन्त टुवर्ड्स द नर्मल भइरहेको छ त. बेन्ड नभएको भए यो लाइन सिधै जाँदैन थियो. अन्त अगर लाइट बेन्ड नभएको भए यो लाइन पछाडि बनाउँदा यता सिधै जान्थ्यो नि त. बेन्ड भयो र त आई क्यान लाइक आइएम एबल टु प्रोजेक्ट द लाइट समवेयर हायर. बेन्ड नभएको भए त you can't like make two paths for a single light. If it's not bending like something like this, then I can't make a light back and go here somewhere. I can't do that. It's not possible. Only if the light bends at a certain point, I can make another path for this light. Okay. Anything else? So there is a bunch of examples given in your book. There are a lot of examples actually. So some consequences of refraction of light. Another topic, sir. So first one is a star appears twinkling in the sky due to the fluctuation in refractive index of air with temperature. So the stars appear twinkling. Stars do not twinkle. Maybe they twinkle because the heat inside the star may change by burning, but the twinkling of stars that we see from Earth is not because the stars are twinkling. That is only because the temperature of our atmosphere changes, and because of the temperature change, there will be change in the refractive index of the medium, the refractive index of air. So when there is dense air and cold air and it's fluctuating, because of that will be the reason why we can see the stars twinkling, right? Second example is sun is seen a few minutes before it rises above the horizon in the morning, while in the evening a few minutes longer after it sets. So morning before it comes out of the hill, okay, before it comes out of the horizon, you can still see the rays of the sun, right? Some part of the hill may be illuminated by the rays of the sun, but still the sun is not seen. Sun will still stay inside the horizon. Now that is because of refraction. Some light will come there and refract into the Earth's atmosphere, and you'll see the rays of the sun more even after the sunset. So even after the sun has set, you'll see some part of the hills to be illuminated, right? It is very evident from our place. It's very easy to notice from hilly areas from where we stay. So even after the sunset, we can see some areas to be illuminated by the rays of the sun. So that is an example of refraction. Piece of paper stuck on the bottom of glass to be raised. A water tank up because shallow.
Sun को उयो हुन्छ नि.
Yes.
हौ त्यो पनि उयो टेम्परेचरले गर्दा नै भएको.
के को सनको चाहिँ?
अब तपाईले भन्नुभयो.
No, sunको refraction is not because of it is because of temperature. Temperature चाहिँ गर्दा fluctuate हुन्छ. तर the main reason why is the most of the distance that the sun ray travels is through space, right? Space is nothing. It is like speed of air is, speed of light is 3 into 10 to the power 8. There will be no effect on the speed of light. It will come without refracting anywhere. But as soon as it enters the atmosphere of Earth, हजुर, action. As soon as it enters the atmosphere of Earth, the atmosphere of the Earth is thicker, right? It's a denser medium. So light is coming from the sun and it's traveling through space. So space ma travel गर्दैछ भने it's the rarer medium because there's nothing in space. But once it comes in contact with the atmosphere of Earth, the atmosphere of Earth is composed of air. It is not vacuum. So now that becomes a denser medium. Because of that, the ray that enters through the atmosphere will undergo a phase of refraction on the boundary between space and atmosphere. That is the reason why all these things happen.